and welcome to episode 3 of Doing Research in Psychology Advanced. Okay, so before we get started today, let's briefly recap some of the things that we covered last week. So if you remember, we talked about the third variable problem. So this is this idea that in correlational research in particular, there are often unknown, unmeasured third variables or lurking variables that can potentially explain the relationship that we're seeing in our data. So that is, correlation doesn't infer causation, and making causal inferences from correlational data can be particularly hazardous. So we need to take care to make sure that we're measuring and accounting for as many third variables as we possibly can when we run a correlational study. And we also learned about signal detection theory. So this is where we have those two ways of being right, so hits and correct rejections, and also those two ways of being wrong, so misses and false alarms. And signal detection theory is really sort of a useful sort of metaphor or framework for thinking about the sorts of decisions we make every day under conditions of uncertainty. But it's also a really useful way of thinking about hypothesis testing in psychological research, where we also have a bit of uncertainty, where we can be right and wrong in the conclusions we make about significant findings. So a hit in the context of hypothesis testing is correctly inferring that signal is present, that the effect or relationship that we're seeing in the data is genuinely out there in the world. Whereas a false alarm, on the other hand, would be inferring that there is signal present out there in the world, when in fact what we're dealing with is pure randomness. So we reject the null hypothesis that random error variance is explaining the pattern of results that we're seeing, but we've made an error in that decision. And so false alarms in our hypothesis testing context are what we refer to as type 1 errors. And then we have correct rejection. So this is where we correctly reject that there's signal present in the world. So we correctly retain the null hypothesis that random error variance is explaining the pattern of data that we're seeing. And then finally we have misses. And so this is what we refer to as type 2 errors in hypothesis testing. And so this is where we've retained the null hypothesis, so the chance explanation for our data, or the random error variance explanation for our data, when in fact there is a genuine relationship or effect out there in the world, and we've just failed to detect it. So really the ultimate goal in designing an experiment or a study in psychology is to increase those two ways of being right and to decrease those two ways of being wrong. But the take-home message really is that there is this uncertainty inherent in this process of finding things out about the world, that we can be wrong about the inferences we make. And we want to try and minimize those errors as much as we can in research with various different methodological tools and statistical tests and procedures. Okay, so with those things in mind, today we're going to go over simulating randomness. So we're going to get to know what randomness looks like. Then we'll take a look at designing experiments in psychology in such a way that allows us to better control for randomness, random explanations for our data. And then finally, we'll look at some of the ways in which we can measure and quantify differences between conditions and groups in experimental research in psychology. Okie dokie, let's start with simulating randomness. So whenever we test hypotheses in psychology, we tend to compare our sample of data to what we might expect to see due to chance. But let's get to know chance a little bit better. Let's get to know that null distribution a little bit better. So let's start by talking about the law of large numbers. So this is a topic that Danny Kahneman has focused a lot of his decision-making research on. So in one of the earlier chapters of his book, Thinking Fast and Slow, he talks about an example of the law of large numbers involving kidney cancer. And so he talks about the incidence of kidney cancer by town and county in the United States. And so interestingly, in this example, one of the towns in the US with the lowest rates of kidney cancer tended to be rural, sparsely populated, and located in a Republican state. So really this is a beautiful demonstration, a beautiful example of how easy it is to tell a story when we're faced with some phenomena that needs explaining. like this extremely low rate of kidney cancer in comparison to the rest of the country. So it's easy to dream up various different explanations for why we might see such a low rate of kidney cancer in a small town. Perhaps there's no pollution, or there's fresh, clean air and water. So you see, it's pretty easy to come up with these causal explanations for the data. But there's a catch, as always, and in this particular data set, the towns with the highest rates of kidney cancer also tended to come from rural, small, sparsely populated states in the US. So how can this be? How can the smallest towns in the US contain the highest rates of kidney cancer and the lowest rates of kidney cancer? How can we explain this data? Well, it's easy to come up with causal explanations again. So maybe these towns have poor healthcare or lower incomes or higher fat diets. But both explanations can't be correct. The problem is we're explaining something that doesn't need to be explained. We're dealing with a situation of the law of large numbers. So the simplest, most parsimonious explanation here is that kidney cancer rates vary randomly. And it just so happens that in smaller towns and smaller populations with fewer observations, so fewer patients, random variance can look systematic. And that's the law of large numbers. Chance is lumpy, particularly in small samples of observations. So let's unpack this a little more with another example. Now let's imagine that our sorting hat from Harry Potter is pulling houses out and assigning houses to people purely at random. And let's imagine even further that this particular year, Hufflepuff and Ravenclaw are full. That just purely by chance, all of the marbles that are assigning people to those two houses have already been drawn. So all we have left in the hat are red marbles for Gryffindor and green marbles for Slytherin. And so here's the problem. Imagine a sorting hat filled with marbles. So we have half red marbles and half green marbles. Harry draws 4 marbles on each trial, and Hermione draws 7 marbles on each trial. And they repeat this process of sampling 4 or 7 marbles out of the hat multiple different times. And both of them record each time that they draw either all green marbles or all red marbles. How likely is it that Harry will draw a streak of 4 red or green marbles versus how likely is it that Hermione will draw a streak of 7 red or 7 green marbles? So it turns out that Harry will actually draw streaks of red or green marbles 8 times as many as Hermione. So Harry will draw 4 in a row on 12.5% of samples, whereas Hermione will only draw 7 in a row on 1.56% of trials. Now, that's a pretty big difference, and people find it particularly difficult to appreciate this property of randomness. That is, that the chance is lumpy, particularly in the short run. And so the chances of getting all red or all green with 4 draws, so 4 samples of marbles, is much greater than getting all red or all green with 7 draws of marbles. So smaller samples are lumpier. And the flip of that is that large samples are less lumpy. So that's the law of large numbers. With enough samples, the ratio of red and green marbles will approximate their true probability, which in this case is 50-50. We've got 2 particular options and they're both equally likely. So the probability of drawing a red or a green marble in the long run, if we take enough samples, is about 0.5 or 50%. So let's look at this idea of the law of large numbers in a slightly different way, and this example in a slightly different way. So Harry here has 4 coins, and they're unbiased, so you'll notice that the probability of flipping a heads or a tails is 0.5 or 50%. And so if he flips those 4 coins enough times, let's say that flipping those coins is sort of like running an experiment. Let's say he runs that experiment of flipping those 4 coins 1,000 times. Then we can see in the long run that the probability of flipping all heads or all tails is about 60 out of 1,000. It's not impossible. You can still get a streak of heads and tails 60 times out of 1,000 in this particular case. So that's with 4 observations. But what about Hermione? So Hermione's got 7 coins, and they're unbiased as well. So the probability of flipping a heads or a tails is again the same, so about 50%. But she's got a larger sample. She's sampling more coins on every single experiment she runs. And so let's say that she runs exactly the same experiment. It's just that on every single experiment she runs, she's flipping 7 coins instead of 4. And we can see with Hermione's simulation that in the long run, occasionally we can get 7 heads in a row or 7 tails in a row about 8 or 9 times out of 1,000. So this really puts it into perspective, right? So we've got a difference between 8 or 9 all heads and all tails versus 60 all heads and all tails, just by increasing our sample size from 4 coins to 7 coins. So a relatively small increase in our sample can have a pretty big impact on our estimate of probability. But nothing quite beats seeing this with your own eyes. So in your research projects, there's an example task of simulating a random coin flip. So in this particular case, we're using the R binomial function to simulate 10 coin flips at a time with a probability of 0.5. So we've got an unbiased coin, and if we were to run this code chunk multiple times, we'd see the number of heads and the number of tails that we flip on every single simulation changes. So I'd encourage you to give it a go and see how many simulations it takes for you to generate a streak of all heads or a streak of all tails. So in this particular simulation of 10 coin flips, we have 6 heads and 4 tails. But see if you can repeat this simulation multiple times. How long does it take before you get a run of heads or a run of tails? What if you change the size of your sample from 10 to 1,000 to 100 to 4? What we're dealing with here is the binomial random generating process. And it's the null hypothesis that we're comparing to when we run a significance test. And it's the null hypothesis that we're comparing to when we run a significance test. We want to make sure that the variation or the pattern or the relationship in our data isn't just due to this binomial random generating process. Okay, so let's bring this back to our kidney cancer example. So some towns have smaller populations. So this is similar to Harry's smaller coin samples. Remember, he's flipping 4 coins at a time. And some towns have larger populations. So this is similar to Hermione's larger coin samples. So remember, Hermione has 7 coins that she's flipping on every single experiment. And each town represents a signal sample with a single rate of kidney cancer. And extremely low and extremely high rates are similar to our all red or our all green streaks that we're pulling out of our sorting hat. So in this scenario, will the small towns or the large towns have the highest rates of kidney cancer? What about the lowest rates? Have a think about this for a second. So it's a little bit counterintuitive, but in fact, the smaller towns will have more extreme rates of kidney cancer because chance is lumpy in the short run, and those small towns have smaller populations. They're equivalent to smaller runs of heads and tails. Whereas with the bigger towns, they're analogous to flipping many, many, many more coins that give us a much tighter estimate of the probability of kidney cancer. So in shorter runs, in smaller populations, we're much more likely to see extreme scores because our samples are much smaller. This is the law of large numbers. The bigger the sample, the more closely you can estimate the probability of the particular outcome that you're interested in. So here's a slightly different way of thinking about it again. Assuming that the following are records of births in a hospital, and that boys are roughly equally likely as girls to be born, rank the following sequences as to how likely you think they are. What do you think? Would you be most likely to see that a streak of all girls, a streak of half girls and half boys? Will it be lumpy? So will you get several girls in a row followed by several boys? Or will it chop and change a little bit more? So will you get a girl and then a boy, girl and a boy? Which one of these sequences is more likely? So if G and B are equally likely independent occurrences, the average in the long run should be 50-50, or 0.5 out of 1. But these are pretty short sequences. Now, I think the intuition is that there's something wrong with the streak of all girls, but each of these sequences are actually equally likely to occur. Now, let's break this down a little bit more. Let's bring in our sorting hat to help us think through this. So if we were to put every combination of girls and boys into the hat, there'd be 64 possible sequences of 6. But remember, we've set our sorting hat to be completely random, so this means that every single possible sample that we could possibly draw from the hat is equally likely to occur. And that includes our strings or sequences of all boys and all girls. They're just as likely to occur as strings or sequences of boys and girls that alternate. So each of the 64 possible sequences is equally likely to be pulled out of the random sorting hat. Okay, so those are some examples of the law of large numbers and the surprising streakiness or lumpiness of chance and randomness, particularly when we're dealing with short runs or short samples of observations. So let's jot down some of the key concepts we've just gone over. So we have the law of small numbers. So with few instances or few observations or a small sample, we can get multiple runs or streaks of the one outcome purely just due to chance or random generating processes. And so in the short run, anything can happen. And then we have the flip of this, which is the law of large numbers. So with many instances, with a larger sample, chance tends to even out. Events converge on their average probability. So we can much more accurately estimate the probability of an outcome occurring when we have a larger sample of observations. And so this is why we want lots of different trials and lots of different participants in our experiments, because it allows us to much more accurately and precisely measure the probability of a particular outcome. We get much closer to the true probability of things when we're dealing with larger samples. And so there are two main features of a random binomial distribution. One is that the outcomes are independent. Remember, we're dealing with random independent error variables. And the second feature is that they have a constant probability. So a coin flip, for instance, has a constant probability of 0.5. But you need a large enough sample to accurately estimate that probability. So one of the take-homes here is we often fail to appreciate how lumpy chance can be. We have an intuition that when we're dealing with random variation, that we're going to see far more alterations than we typically do when we're dealing with random data. And the gambler's fallacy is a great example of this. So this is a mistaken belief that if something happens more frequently than normal during some period of time, then it will happen less frequently in the future. Or alternatively, if something happens less frequently than normal, then it'll happen more frequently in the future. So for example, upon seeing 6 straight occurrences of black on a roulette wheel, a gambler suffering from the gambler's fallacy, this illusion, would confidently bet on red for the next spin, even though red and black are equally likely to occur on every single spin of the wheel. And so siblings are another example of the gambler's fallacy. If we have 3 boys, what are the chances of having another boy? What about a sequence of 2 boys and 1 girl? Are we likely to have a boy next or a girl next? Does it feel like in the first sequence we're more likely to have a girl next because we've had 3 boys in a row? Again, this is a situation where both outcomes are equally likely to occur. And again, let's look at this from our coin flipping example. What if we were just due to chance to flip a long run of tails? What would happen next if we flip our coin one more time? What would be more likely, a tails or a heads? Well, even though it feels like we might be expecting a heads coming up, in fact, both are equally likely. Whereas if we were to encounter a sequence like this, which alternates more between heads and tails, we wouldn't feel that same intuition. We feel much more confident in the randomness of our coin, even though both of these sequences are equally random. So that's the law of large numbers. Another important concept when we're talking about random generating processes is regression to the mean. So Galton referred to regression to the mean as regression to mediocrity, and he used the quincunx to demonstrate regression to the mean. So here, a bag of pellets are poured through the little opening at the top of the quincunx. And so they make their way randomly through the quincunx and settle at the bottom, forming a nice, neat, normal distribution that approximates the binomial random generating process that we've been learning about. And so Galton's question was, from where did these pellets come? And the answer is, on average, more towards the middle. So the central tendency, the mean, the median, and the mode, is our best predictor given a normally distributed set of measurements. So this is regression to the mean. And Kahneman uses the example of a conversation he had with a pilot instructor who made the following comment on the effects of praise versus punishment in pilot training. So on many occasions I've praised flight cadets for their clear execution of some aerobatic maneuver. And in general, when they try it again, they do worse. On the other hand, I've often screamed at cadets for bad execution, and in general, they tend to do better the next time. Right? So this beautifully illustrates regression to the mean. Imagine the flight instructor knows all of the distributional characteristics of the cadet's performance in the long run. He might observe, purely due to chance, that the good and bad maneuvers, in the first instance, are actually just an outlier, an extreme case in the distribution of their performance. And so the next observation, given that we're dealing with some random variance in their performance, is actually likely to be closer to their mean performance overall. It's likely to regress to the mean. And so this observation that cadets do worse or do better in response to praise and punishment could actually just be an artifact of regression to the mean, an artifact of randomness and not punishment or praise per se. Now think of regression to the mean with respect to performance at a job interview. There are many independent random variables that can now affect our performance on the day. Maybe we didn't get a great night's sleep the night before, or we missed breakfast, or our bus was late. There are many different reasons why we might not be performing at our best. So sometimes it feels like the world is conspiring against us, resulting in below average performance. But the flip side of that is that the world can also be working with us, that these random independent variables can also be conspiring to produce an above average performance on the day. But the point is that this variation in our performance is completely random, and that the factors or the variables that are influencing our performance from one time to the next are almost always independent from one another. Or another way of putting this is the extreme performances in the long run aren't very frequent by definition. Average performances, by definition, are the most frequent in the long run. And so consider this with race times in swimming. One race doesn't really tell us much. The swimmer might have a cramp, or their goggles might be filled up with water, or they might still be jet lagged from a long haul flight. Unless we have a larger sample of observations, we just don't know if the race time we're looking at, the observation we're looking at, is an extreme observation, is an extreme performance, or if it's a more typical performance. And so what this demonstrates, this idea of regression to the mean and the law of large numbers, is that we need to be cautious when we jump to causal explanations, systematic explanations for single observations. An increase or a decrease in performance from one race to the next could simply be due to regression to the mean, or pure random variation. Okay, so here's a thought experiment for us to try. Let's say we have a class of 100 students who take an exam on their first day of class. There are 100 true-false questions written in gobbledygook, which is the language of the goblins. But nobody can understand this particular language, and so they respond randomly to the question. So they randomly select true or false for every single question on the exam. So every member of the class responds randomly on the exam. Now, most people are going to perform at about 50% on average, but some students are going to perform at the tails or the extremes of the distribution, so that they might perform better or worse than 50% just due to chance. Remember, they're responding randomly on this exam. And so the top student, just by chance, say Hermione, scores 65%. And the bottom student, just by chance, let's say it's Harry, scores 35%. Now, let's think about this. How are Hermione and Harry likely to perform on the final day of class when they take a second exam with 100 new questions written in gobbledygook? So they're sitting another exam with another 100 questions where they're responding randomly again. Who's likely to perform better or worse? Or what's going to happen to Harry's score versus Hermione's score on that final test, given what we've just learned about regression to the mean? So I'll give you a minute to think about that. Pause the recording, and then we'll get back to it. Okay, so the key here is that Harry and Hermione are the most extreme scores in this random distribution that we've just generated. And so running the test again, the most likely thing that's going to happen is that their random responding will be closer to the average. So Harry's score is most likely to regress towards the mean of 50%, so his score will likely go up, and Hermione's score is also going to regress towards the mean, so it's most likely to go down. Right? So regression to the mean is simply when we have a variable that is extreme in its first measurement that then tends to be closer to the average on its second measurement. And so if it's extreme on its second measurement, it will also tend to be closer to the average on its first measurement. And then we also have this idea of random independent variables, or random error variance, as it's also known, where we have many different things that can influence our measurements besides the things we're interested in measuring. And then there's this idea of measurement error. So regression to the mean is actually greatest where we have less precise measurements. So the greater the error variance, the more random independent variables that are at play, the less precise our measurement, and the more likely there is that we'll see regression to the mean from one observation to the other. And again, see if you can observe this phenomena of regression to the mean using your R binom function within R. So you may, for instance, get an extreme sample on your first simulation. So in this particular case, we have, say, 1 tails and 9 heads. But we know we're dealing with a fair coin that has a probability of 0.5. And so what should happen next on the next simulation? What will happen to the heads and tails? Will they go up or down? Chances are they'll regress towards the mean probability for this particular coin. Okay, so those are some properties of randomness. So let's take a brief look at designing experiments in psychology. So last week we talked about how it's really difficult to isolate the causal mechanisms that are at play with correlational research. And one of the answers to that problem is to run a randomized controlled experiment. And so what kinds of designs or experiments are we talking about here? So generally, we have 2 different kinds of experimental designs that we can use. We have between subjects designs. So this is where different participants are assigned to different levels of our independent variable. That is, participants are nested in the different conditions of your experiment. So let's say we have a treatment and a placebo or a control, and as a participant, you are randomly assigned to one of those conditions or groups only. So that's a between subjects design. Another common design is the within subjects experimental design. So this is where the same participants are repeated in every level of our independent variable. So that is, participants are crossed with the different conditions of our experiment. So experiments are better than observational and correlational research for controlling for random error variance, but not all experiments are equal in their ability to control for random error variance, and experiments aren't immune to the influences of random variation impacting on the measurements we use. Within subjects designs, for instance, are much more powerful than between subjects designs because we can control for the random error variance that's introduced via individual differences when we assign people to different groups. Okay, so let's try a few different designs on for size. This one here is a between subjects design. So one of my honours students last year ran a project looking at the perceptual expertise of fingerprint examiners. And so she compared the performance of really experienced fingerprint examiners who have a lot of experience looking at fingerprints to a group of novices who've never seen a fingerprint before. And she compared the performance on a fingerprint classification task. So they were given a fingerprint and they had to decide whether or not it was left by a left or right hand, and if it was left by a thumb, an index, middle, ring, or little finger. So her dependent variable here is classification performance, and her independent variable is group, whether they were from the expert group or the novice group. And because they're only in one of those two groups, they're nested within each of those groups, we call this a between subjects design. Okay, so let's take an example of a within subjects design for comparison. This one is a project that one of my honours students this year is working on. So there's this idea of visual crowding. So when you try and identify an apple or a letter in your peripheral vision, it's much harder to recognise it when it's surrounded or flanked by other objects than when it's presented in isolation. So this is what we call visual crowding. And so in this particular experiment, participants see multiple different images that are presented in their peripheral vision, and they're either surrounded by other objects or they're presented in isolation. But critically, all of the participants see all of the different conditions in the experiment. So this is what we refer to as a within subjects design, where we're comparing participants to themselves across their different conditions. Right? So the defining characteristic of a within subjects experiment is that the same participants are used in every condition of the experiment, including the control condition. And so these sorts of designs are desirable because we don't have to worry about a random error variance due to using different subjects in different conditions. So this is an example of a true controlled within subjects experiment, where we're comparing the average scores of participants across two conditions that differ on some particular variable of interest. In this case, whether or not the objects presented in peripheral vision are flanked by other objects on. So we've wiggled our independent variable, whether or not we've crowded objects in peripheral vision or not, to see what effect it has on our dependent variable, people's ability to recognize those objects in their periphery. In these sorts of cases, we have fine control over the causal influences that are resulting in the differences we see across the different conditions. But it's not always possible to manipulate things and to wiggle events. And so sometimes we have to settle for comparing observations that fall naturally across different conditions as opposed to randomly assigning them. But the trade-off there is that the causes of the behaviour of interest are less well understood. The pure chance explanation or the random error variance explanation remains somewhat viable, even after a lot of good detective work. And so this is why it's almost always best to manipulate our independent variable, if we can, if it's ethical to do so. And so sometimes, even though we may not be able to manipulate our independent variable of interest or conduct a fully within subjects design, there's still ways in which we can design our experiments to minimize the impact of random error variance. And so one such design choice we can make is to match participants on particular variables across key conditions in our experiment. So we call this a matched pairs design. So a really good example of this particular design is research comparing experts and novices in a particular domain. So we're interested in knowing whether or not experts are better than novices on some particular task, but we want to control for potential differences between those two groups that might explain any expert-novice difference that we find. And so we can match each of our experts to novices on particular elements we want to control for. So for instance, every expert-novice pair might see the same sequence of trials in an experiment. They might see the same images and respond to the same stimuli and materials in the experiment. Or you might match the expert-novice pair on their age and level of education, depending on the sorts of things we want to rule out as potential explanations for any differences we might see between those two groups. Right, so it's not a fully within subjects design where every participant participates in every single condition, but it's a matched pairs design where every pair, expert-novice pair in this case, participates in every single condition. And so the advantage of using a matched pairs design is it allows us to control for random error variance. So potential differences between the population that we're not interested in that might explain our results. One of the disadvantages is it can be really hard to find matched samples of participants. It can be time-consuming and resource-intensive. But if it's possible to do so, these can be really, really powerful designs in the absence of being able to run a fully within subjects design. Another slight variant on the within subjects design is the pre-post design. So this is a typical case where we don't always have complete control over our independent variable of interest. And most of the time, this involves some sort of measurement of change over time. So we're measuring something at different points in time and seeing whether or not there's a difference between those two measurements. So for instance, we might want to know whether or not taking a particular course results in improvement in learning. And we might want to compare our performance on some measure before and after the course. This would be a pre-post design. Another example might be a treatment experiment in clinical psychology, where we're interested in knowing whether or not we see a change in patient outcomes before and after a particular treatment. But without a proper comparison group, without a control, it's difficult to know whether or not the treatment or something else that happened at the same time is resulting in that change from time A to time B, from the pre to the post-test. And so in these sorts of pre-post experiments, it's pretty important to have a control group. And in some cases, we need more than one control. So particularly in the development of treatments, so particularly in randomized controlled trials, often it's important to have a placebo condition, for instance, where you have one group of participants who receive the treatment that you're interested in measuring, another who receives no treatment, and another again who receives a treatment, but that doesn't include the active ingredient that you're interested in isolating and manipulating. So it's sort of like the sugar pill control. Okay, so one last thought experiment to think about the differences between these two kinds of designs. So let's say we have an experimenter who wants to test the effect of noise on our analytic problem solving. So let's say she divides her participants in half. So she puts half of them in a noisy room and half of them in a quiet room. And then she compares how fast and accurate they are at solving various different puzzles and problems. So what are the chance explanations that we're dealing with in this toy experiment? Well, because we've randomly assigned participants to noisy and quiet rooms, we're actually comparing apples with oranges. So in addition to random variance that might affect any given participant's performance, we also have to worry about random sampling processes that might affect our results. So just due to chance, we might have individual differences between those two groups that could explain differences in their problem-solving performance. And so the main strength of a within subjects design is that we're comparing apples with apples. So for example, as an experimenter, if we were to use a within subjects design, we wouldn't have to worry about all of the, say, smart people ending up in one group or the other, because everybody is in all of the groups. So by comparing everybody to themselves, we can really isolate the effect of noise on people's problem-solving ability. Okay, so to activity 4. See if you can come up with an example between subjects design, within subjects design, matched pairs design, and a pre-post design, so that we can start to build a repertoire of what these different experimental designs can look like in different contexts. So within subjects designs are often the gold standard, if it's possible to run them, because they allow for us to control for all sorts of random variation. But really, when it comes down to making design decisions in psychological research, what we're doing is trying to rule out various different chance explanations for our data. Remember, what we're really trying to do in research is tell the difference between pattern that is genuine and pattern that can be explained by random variation and other extraneous factors. And so our best defense against pure chance explanations for data are within subjects designs, and if we can't, or if it's not possible to run a within subjects design, then a match pairs design. And if neither of those options are available, a between subjects design is still useful for isolating causal variables, but we just have to be a little bit more mindful of potential chance explanations for our data. So to that end, let's take a look at how we actually measure differences between conditions and groups when we run these different kinds of experiments. So one of the first things we might want to do is to compare our sample of observations to a particular mean. We have a couple of options. We can run a one-sample t-test or a one-sample Wilcoxon rank sum test. So with both of these, we make a few assumptions. With the t-test, we're assuming that the independent variable is on a continuous scale, that the observations are independent of one another, the dependent variable should be approximately normally distributed, and the dependent variable should not contain any extreme outliers. But if our data aren't normally distributed, then we might run the Wilcoxon rank sum one sample test instead, with fewer distributional assumptions about our data. And so both of these are fairly straightforward to run in R. The functions that we're mainly interested in here are the t-test function for the one sample t-test and the Wilcox test function for the Wilcoxon rank sum. So we input our data frame, indicate our dependent variable and independent variable. Mu indicates the level of chance that we're wanting to compare our sample against. So in this case, a chance level of 10%. An alternative is where we indicate whether or not we want to run a two-tailed test or a one-tailed test. Now, most of the time we would run a two-tailed test, but with these one-sample tests, it's sort of a rare exception where when we're comparing to chance, most of the time we expect or predict above chance performance, whereas we wouldn't expect systematic deviation from chance in the other direction. And so we can pull our 5% error rate, our alpha rate, into that one upper tail of the distribution in this particular case. And we'll go into why we might choose two-tailed tests and one-tailed tests a little bit later on. But for now, these are the two tests we can use to compare mean performance to chance performance. And which one we choose really depends on the nature of our data. Another common scenario we might face in experimental research is a scenario where we want to compare two different means. So again, this really depends on the kind of test we run will depend on the design we have. So let's stick with our unmatched, unpaired, between subjects experiment comparing novices and experts in their fingerprint discrimination performance. So we have two groups, novices and experts, and we want to know whether or not experts are more accurate than novices. What test would we run in this particular situation? So here we have an independent samples t-test, or alternatively, the non-parametric version, which is the Mann-Whitney U test, which is exactly equivalent to Wilcoxon rank sum, if you hear that one around as well. So again, here we're making a few assumptions about our data, and we want to make sure our data meet these distributional assumptions before using these tests. So with the independent samples t-test, we're assuming three main things. Firstly, independence. So we need two independent categorical groups that represent our independent variable, in our case group, so expert and novice. We're assuming normality, so that means that the dependent variable should be approximately normally distributed. The dependent variable should also be measured on a continuous scale. And we're also assuming homogeneity of variance. This is also sometimes referred to as equality of variance, where the variances of the dependent variable across our two groups should be approximately equal. Now, if our data severely violate these assumptions, then an alternative test we can run is the man-Whitney-U, which makes fewer distributional assumptions about the data. So there we're still assuming independence, that we have two independent categorical groups that represent our independent variable. And we're also, but our assumption about the scale that we're using is more relaxed. So our data could be on a continuous or an ordinal scale. And these tests are also pretty straightforward to run in R. So we can use the same base R functions to run these tests, so the t-test function and the Wilcox test function. Except this time we're specifying our data, our dependent variable, and then both levels of our independent variable. So in this case, novices and experts. And this time we've set our alternative to a two-sided test because it's plausible that novices might be more accurate than experts, or experts might be more accurate than novices. So we want to distribute our error variance across the two tails. And importantly, because we're dealing with a between subjects design, we set paired to false. So this means we're dealing with independent observations across those two levels of our independent variable. And we can see the output of our tests are very similar again. So these tests return an exact p-value and confidence intervals as well. And so if we find a p-value of less than 0.05, this is the decision rule we use to conclude whether or not there's a significant or meaningful difference between the two means that we've measured. So that's the independent samples t-test and man-Whitney-U test. But what if we have a matched pairs design or a within subjects design where we want to compare two means? What do we do in this sort of scenario? So here we have a paired version of the t-test and also a paired version of the man-Whitney-U, which is commonly known as the Wilcox and signed rank test. So the assumptions here that we're making about our data are slightly different. With the paired samples t-test, we're assuming that the data are dependent this time. So that means that the independent variable consists of two categorical related groups or matched pairs. Remember the observations, so each expert is paired to a novice in our matched pairs example. We're assuming normality again, but this time this is referring to the distribution of the differences between our two groups in the dependent variable. So we want to know whether or not the difference between each of our expert and novice pairs across expert and novice pairs is normally distributed. And finally, we're also assuming that we don't have any extreme outliers with these tests as well. Now, if our data severely violate any of these assumptions, so let's say we have highly skewed data, then one alternative is the Wilcox and sign rank test that makes fewer assumptions. So back in RStudio, to run these tests, it's pretty much the same as the independent samples tests, except we're specifying paired to true instead of false. So this is indicating that we're dealing with paired data instead of independent data. But everything else remains the same. And finally, another alternative to the t-test or Wilcox and sign rank test is the permutation test. So permutation tests work by resampling our observed data without replacement many times in order to determine a p-value for our test. So The difference here is instead of assuming the distributional nature of our data, instead of assuming we're dealing with the normal distribution of difference scores or observations, we're actually building or estimating our distribution by shuffling our data around. So recall that p-values are defined as the probability of getting data as extreme as the observed data when the null hypothesis is true. So if the data are shuffled many, many times in accordance with the null hypothesis being true, the number of cases with data as extreme as we've observed could be counted, and we can calculate a p-value based on that estimated distribution. Right, so this is a slightly different approach to inference, where we're estimating our population distribution rather than assuming it. Right, so a really neat way to see what happens when you permute your data is to use the sample function in R. So if you specify the data frame that you want to sample from, set replace to false, and then put your sample in a completely new variable and print that variable out, you'll see that your data have been shuffled around. Now, all that's happening with the permutation test is that we're doing that many, many more times. And then there's a package called the easy package that contains a permutation test function. So that's the easy perm function there. And if we specify our data, our dependent variable, our participant variable, our independent variable, and the number of permutations we want to run, in this case 1,000 permutations, and then click run, we get a p-value that we can interpret. Right, so those are a few different ways in which we can compare different means. But what if we have more than two means in our variable? What if we have more than two levels to our variable? How do we figure out where the differences lie? So this is where we'll pick up on next week, and we'll also cover situations where we might have more than two variables. And then we'll delve into p-values, stepping through the logic of hypothesis testing in psychology, and other ways in which we might estimate the magnitude of an effect and interpret the meaningfulness of an effect. So it's easy to mistake purely random sequences for systematic variation, particularly in those smaller samples of observations. So remember, chance can be lumpy, that we can see long runs of particular outcomes, particularly in small samples, just entirely due to chance. So be wary of claims made with data based on really small samples of observations. Chances are that chance could be a pretty good explanation for the data. Okay, I'll see everyone in class.